Up till now we've been dealing primarily or solely with single degree of freedom systems, where you have one mass, one spring generally, and one damper if there's damping in the system. We're now going to move on to more than 1 degree of freedom. This chapter, chapter 5, is going to be stuff that you may have seen before in level 2 dynamics. Okay, we're going to go over a revision of 2 degree freedom systems. There might be some extra things in this chapter that you haven't seen before. Okay, and then we're also going to talk a little bit about what about more than 2 degree of freedom systems, 3 degree of freedom systems in particular. Okay, so this is going to sort of cover the basics. How do you find the equation of motion? How do you find the natural frequencies and the mode shapes? What do those various terms mean? Okay, and we'll cover, like I said, 2 degree of freedom systems, semi-definite systems, and then 3 degree of freedom systems as well. And then in the following weeks we're going to look at other ways that we can deal with more degrees of freedom and approaches or methods that we can use to deal with those systems. So this is chapter 5, multiple degrees of freedom. So like I said, look at 2 degree of freedom systems first. How do we find the equation of motion, natural frequencies, mode shapes? That stuff you should have seen before. Okay. Look at the general solution for those systems. We're going to go through an example, a brief example, shouldn't take too long. Then we'll look at semi-definite systems or degenerate systems and what's the difference and how do we approach those problems. And then I'll do a little bit on initial conditions and how we can find those arbitrary constants that we end up with in the solutions. And I'll then move on to 3 degree of freedom systems, which you can take the same approach, just there's a little bit of added complexity there, which you'll explore, and we'll do an example to demonstrate what's going on. So, this is a typical schematic of a 2 degree of freedom systems. We have 2 masses, M1 and M2. Okay, we've got 3 springs, K1, K2 and K3, and they're connecting the masses to each other and to ground. Okay. This particular schematic has damping in, so we've got dampers in there. The displacements of mass 1 and mass 2 are indicated by x1 and x2, and in this situation, if we had forcing functions on the masses, then they're denoted by F1 and F2. So this is the general 2 degree of freedom system. Okay. So, to find the equation of motion, we can simply employ Newton's second law if we wanted to. So, for the first mass times acceleration is the sum of all the forces. Well, you add up all the forces. We've got our applied force, F1. Then we've got the damping force, C1. Okay, then there's the second damper, we have C2. And because that second damper is between the 2 masses, C2, you can see it's between the 2 masses, we have to take the relative difference in velocity between the 2 masses, which is why we've got x1 dot minus x2 dot. Then we've got K1, which is the mass connecting mass 1 to the ground, the spring, and then the K2 is the spring connecting between the 2 masses, again x1 and x2. And so we've got this coupled equation. Basically, you can see we've got mx double dot, mx1 double dot, okay? But in the equation, in the resulting equation, we're going to end up with, we've got, let me point to it, mx1 double dot, then we've got some terms in terms of x1 dot and x2 dot, and x1 and x2. So this is the equation of motion, okay, but like I said, you can see that it's coupled. It's not solely working in terms of x1. You have to know what's happening to x2 to solve that equation. Fortunately, we've got an equation for x2, which is the same thing here. Again, if it's between the 2 masses, then you have to include them both. Okay. So x2 dot minus x1 dot for that damper, and this one for the spring. So if we go back to the picture, if we look at mass 1, you've got mx double dot, okay, which is the inertia, equals this spring force times that displacement, and this damping force times that velocity. Okay, that's all contained within x1. But you've also got to include the spring force and the damping force here, and that's going to be the relative displacement between these two for the spring, and the relative velocity between those two for the damper. That's for x1 dot, x1. And then for the second mass, x2, you obviously have these two which are purely related to what's happening to x2, but then these two also will affect what mass 2 does. Okay, and they're going to be, again, the relative displacement between the two and the relative velocity between these two. So that's why you end up with these two coupled equations, this one here and this one here. They're the equations of motion. This is quite a cumbersome way of writing the equations of motion because you have to sit and read it and to work out which ones you're good doing. It's much easier to actually write it in terms of matrices. And so this is the equation of motion in matrix form. We've got our mass matrix up here. This is our acceleration vector. Okay, notice the matrices are in square brackets, the vectors in general are in curly braces. Okay. We've got mass matrix times our acceleration vector, ma, mass times acceleration. Then we have our damping matrix multiplied by our velocity vector. And then we have our spring matrix, or stiffness matrix, multiplied by our displacement vector, and that equals the applied forces. Okay? Now if you remember back when we were looking at single degree of freedom systems, this is mx double dot plus cx dot plus kx equals f. Well, this is exactly the same, except for we can accommodate in this one equation 2 degrees of freedom. And obviously, if you up together with matrix multiplication, if you multiplied these equations out, you'd end up with two equations which match up with what was on the previous slide. Okay, that would be m1 times x1 double dot plus 0 times x2 double dot, so that's just obviously m1x double dot, and so on. And you can just go through and multiply them out, and you end up getting the same equations that we had before. And if you were to write this in shorthand, you could write m in square brackets x double dot in curly braces plus cx dot plus kx equals f. Okay, where m is the mass matrix, c is the damping matrix, k is the stiffness matrix, and f and x are the force and the displacement vectors accordingly, respectively. And if you had free oscillation, obviously the applied forces would be 0. And so you just basically replace that vector at the end, the force vector, with 0. Okay, and this is the case for the free oscillation. So that's how you get the equation of motion. You could go through that method of solving Newton's second law and then put it in matrices, but there is a quick method to get to this form straight away, and I'm going to show you that. This may be new. It's basically a way of populating those matrices quickly without having to sit there and go through Newton's second law. The following rules apply. So we've got J and I, okay, this is just basically indices of a matrix, okay. If I take, let's say I've got a matrix called A, okay, A, I will be the diagonals, okay, because I would be 1, I could be 2, so A, 1, 1 would obviously be the first, the element in the top left-hand corner, okay, and A, 2, 2 would obviously be the second one down in terms of the diagonal, okay. 1, 2 would obviously be the first row, second column, okay, that slot. And so here I'm saying that I doesn't equal J. And so for the mass matrix, it's easy. Basically, you say you've got an n degree of freedom system, or 3 degree of freedom system, your mass matrix would be a 3 by 3 matrix, and the diagonals will be populated with the masses. So M11 would be M, the first slot, upper left-hand corner, would be basically mass 1. M22, so the second slot down a diagonal, will be mass 2, and so on, until you get to the end of your degrees of freedom, or your end of your masses. For the damping and stiffness matrices, it's a little bit more difficult. The diagonals are basically the sum of the dampers, or the springs, linking the first mass, so M1 if I was 1, okay, or M2 if I was 2, linking it to ground or to another mass. Okay, it's the sum of them. You add them all up together. So if we went back to that example, let's wind all the way back to our picture. Okay, so we know that the mass matrix would be M1 and M2 in the diagonals, okay? The diagonals for the stiffness matrices and the damping matrices is the sum of the springs, or the dampers, connecting mass 1 to ground or to another mass. And so the first slot in our stiffness matrix would be K1 plus K2, okay? And the second diagonal relating to mass 2 would obviously be K2 plus K3. So that's what happens with the diagonals with those matrices. For the off diagonals, so where I doesn't equal j, and so we've got C12 or C21 and K12 or K21, it is the sum of the dampers and springs that are connecting those two masses together. So if I is 1 and j is 2, then it's the sum of the springs linking mass 1 and mass 2 together. But it's the minus sum. You must include the minus sign. And that basically what you can do just by following those rules, you can find out what M, C and K are. And with these linear systems, they're going to be symmetric matrices. Because obviously the sum of the springs connecting mass 1 and mass 2 is going to be the same number of springs connecting mass 2 to mass 1. So they're going to be symmetrical. And so if we look at this situation, so we had our system, let's draw the system up here. Let's use a bit of a, this is without damping. Okay, so that's mass 1. Mass 2. Okay, and there's ground. K1, K2, and K3. So, the mass matrix, you just take the two masses and stick them in the diagonals, everything else is 0. There's your mass matrix. For the stiffness matrix, the first slot, this one up here, is going to be the sum of the springs between mass 1 and ground or another mass. And so here we've got mass 1, it's going to be K1 plus K2 in that slot there. For this slot, K22, it's going to be the sum of the springs between mass 2 and ground and another mass. So we obviously got K2 plus K3. That sticks in there. And then the off diagonals, you look at this one obviously is between 1 and 2. This is between 2 and 1. Well, you look at what happens. You've got the sum, the minus sum of the springs connecting mass 1 and mass 2 together. So you have obviously minus K2 here. It's symmetrical, so that's minus K2. There's your stiffness matrix. So basically, just by looking at the picture, you can come up with the equation of motion straight away. Okay, just by looking and seeing what springs and what masses are connected to each other. So that's the equation of motion. How do we go about finding the natural frequencies? Now we call it a 2 degree of freedom system because there are 2 degrees of freedom. And because there are 2 degrees of freedom, you're going to end up generally with 2 natural frequencies. Okay? And so we have to go through a process to find these natural frequencies. And the process that we go through is we make a substitution. Now we know that this system is going to oscillate. And so the substitution we can make is the same equation that we had way back in chapter 2 for a single degree of freedom system. Okay? Except for this time, we have this little subscript I, which indicates whether you're talking about mass 1 or mass 2, displacement 1 or displacement 2. And we assume that it's going to oscillate in a sinusoidal way. So we've got a cosine omega t plus phi in there. Okay, and it's going to have an amplitude big X. I've called it X in this situation instead of A just to make it clear what's going on. And so for mass 1, obviously we've got x1 equals big X1 cosine omega t plus phi. And obviously for mass 2 we have the same situation. Omega at the moment is a bit arbitrary. We'll find them in a second. And obviously what we can do is we can take the second derivative of that, okay, and then we can substitute that back into our equation of motion. So that's what I'm going to do next. And what you end up happening is you end up, once you do a bit of simplification, the cosine omega t plus phi disappears because you can divide both sides by that, and obviously that disappears. And then you can combine the two matrices now because they're both in terms of big X1 and big X2. If we look back at this equation, oops, you can see that this x double dot is in terms of big X1, the displacement amplitude. Okay, so because they're both, we get rid of the double dot. It's now not a differential equation, and you combine the two matrices together. Do you want me to show you how to combine those matrices together? Would you like to see that? Okay, so we had, which slide has more space? We'll do it here. So we had M1, 0, 0, M2. And we had x1 double dot and x2 double dot, but now we've got x1, big X2, okay, times by minus omega squared, okay, and they're going to multiply the whole lot in a second, okay, plus, and then we had our stiffness matrix, which from memory was K1 plus K2 minus K2 minus K2 K2 plus K3. Okay, so this is basically substituting these two equations into my equation of motion. And what happens is that we get rid of the x1 double dot and x2 double dot here, and we replace it by this line here. Okay, so we have a minus omega squared term stuck in there. And the same thing happens here. X1 double dot, sorry, x1 and x2, the little terms get replaced by the big ones. Okay, and we have obviously the cosine omega t plus phi, which I've forgotten. Let's call that phi. It's multiplied by both of those terms, or multiplies with both of those terms. And so what you can do, because these are both in terms of x1 and x2, these are both in terms of x1 and x2, you can combine the matrices together. And so we have k1 plus k2 minus m omega squared for the first slot. Down here we've got minus K2, obviously plus 0. Minus K2 plus 0 is obviously minus K2. Down here we've got the same thing, minus K2 plus 0. And then we've got K2 plus K3 minus M2 omega squared. This is M1, by the way. Okay, so is that clear? Basically, these are both in terms of x1 and x2, so you can combine the two matrices together. Obviously, this is going to be multiplied by every term in here. And so we have k1 plus k2 minus m1 times omega squared. These two terms are minus k2 because they're not changed. And then here we've got k2 plus k3 minus m2 times by omega squared, which is in here. And that's multiplied, vector matrix multiplication, by x1, x2. So that gives us what's known as the mechanical impedance matrix. The other way to represent it is to write it in terms of terms. This problem is called the eigenvalue problem, and you may have seen it before. Okay, it's a standard equation. Often this is replaced by a lambda, and we'll do that in a second. It's called the eigenvalue problem. And when you solve it, you'll find what's known as eigenvectors and eigenvalues. Okay? The eigenvalues will be the natural frequencies squared. Okay? The eigenvectors that you can find will be the mode shapes. The way to solve it is to find the determinant of that matrix, that mechanical impedance matrix. Okay? With a 2 by 2 matrix, the determinant, as you are no doubt aware, is basically you take these two terms, multiply them together, and you take these two terms and you multiply them together and you subtract those two from those two. There's your equation. Okay? And what you do is you set that equal to 0 and then you solve for the for omega. So there's our determinant. So those are the diagonals multiplied together minus the off diagonals multiplied together. This is for a 2 by 2 obviously. So you can go through the motions of multiplying things out. It gets a bit complicated, but you know, that's part and parcel of what you've got to do. It's not that tough. Okay? And you end up with an equation here, which is in terms of omega squared. Okay, so you've got omega squared squared, which is omega to the power 4. Here, this whole lot is multiplied by omega squared, and this whole lot is multiplied by omega to the power of 0, obviously multiplied by 1. And so this is a quadratic equation. So we can solve it using the quadratic formula. So if you replace omega squared by lambda, okay, obviously then you can see very clearly it's a quadratic equation. Lambda squared, lambda, and lambda to the power of 0. Here's our A term when we're solving the quadratic formula. This is our B term, and here's our C term. So you can use the minus B plus or minus the square root of B squared minus 4AC over 2A, that quadratic formula, which you should all be familiar with. And it's clear, like I said, that there are two values for lambda, so there are going to be two natural frequencies, omega 1 and omega 2. So there's two natural frequencies, and those natural frequencies are going to relate to different ways that the system can oscillate, different modes of oscillation. Okay, because there'll be one natural frequency that will oscillate in a certain way, and there'll be another natural frequency where the system will oscillate in a different way. And the number of modes of oscillation you have is also related to the number of degrees of freedom. A 2-degree of freedom system will have two modes of oscillation, and I'll show you them in a second. So how do we find the modes of oscillation? Well, you go back to our nice mechanical impedance matrix, and here we multiply the top vector and the bottom vector, or divide the top this vector by x1. Okay, and so you end up with x1 over x1 at the top, which is equal to 1, and you have x2 over x1 at the bottom. And the reason why we do this is this gives us the relative motion of one mass with respect to the other. Okay, which is what we're looking for. We can't find the absolute motion because it doesn't, you know, in terms of how much amplitude you give it to start off the oscillation, it doesn't matter. Okay, it's all about the relative motion between the masses. And so the mode shape is 1 and 1, then obviously you know that if you move mass 1 by x centimetres, mass 2 is going to oscillate around x centimetres as well. And the same thing, if we had 1 and minus 1, you'll see that they're going to move in the same distance but in opposite directions. And what we do is replace x1 and x2 with r, just to simplify things. So there's our equation. And what you do is you take your omega 1 that we found using the quadratic formula and you plug it into the equation. You stick your omega 1 in there, you solve it, because we've got an equation. In fact, you've got two equations you could solve it with, but there's only one unknown. Obviously, if we multiplied this out, we've got k1 plus k2 minus m1 omega 1 squared times by 1 minus k2 r1 equals 0. We know this lot, and we know this. So obviously you can solve for r1. Dot, dot, dot. Okay, so there's one. The other equation obviously is using the second line. It's the same thing. The same answer will come out for r1. And so if we go through the motions, so now by using the values for omega 1 and omega 2, we can find the mode shapes 1 over r1 and 1 over r2. Those are the mode shapes, they're vectors. So this is what I wrote just a second ago. And if you go through the motions, you get this equation here. Since we know what omega 1 is, we can find out what the value for R1 would be. And the R1 corresponds to the first oscillation. And then you basically go through the same motion again, solving for R2. You take the same setup, you stick in omega 2, and you'll find R2, okay, which will give you the second mode of oscillation. So it's basically 3 stages. Number 1, you find the equation of motion. Number 2, you find the mechanical impedance matrix, and then from that you can get the natural frequencies. And number 3 is then you stick the natural frequencies back into that mechanical impedance matrix, and you can find the mode shapes. And we'll go through an example of this in a second. The next thing is looking at the general solution. Now we know from a 1 degree of freedom system we had this as our general solution. Okay, this is back in chapter 2. And here we've got 2 oscillations, 2 degrees of freedom, and you can separate them out. You've got x1 and x2, and this is basically the same equation. We've just got these vectors in here which represent the mode shapes. And the reason we stick them in there is when we combine them together, you end up getting the 2 different equations. So this is the same thing. You've got amplitude times by cosine omega 1t plus phi 1, and then second amplitude multiplied by R2 times by cosine omega 2 plus phi 2. Okay. And so there we go. So x1 is basically you take the top value in the vectors. So x1 equals c1 cosine omega 1t plus phi 1t plus c2 times cosine omega 2t plus phi 2. And then x2 is c1 times by r1 cosine omega 1t plus phi t plus c2 r2 cosine omega 2t plus phi 2. Okay? So x1 is basically the top values and x2 is the bottom values, and everything else is the same between the 2 equations. So, as an example, let's look at this problem. We've got a 2 degree of freedom system. We've got 2 masses that are the same value. They both weigh mass m. We've got 3 springs, all of the same value. They're both of stiffness k. And then the lower mass is x1 and the upper mass is x2. And they move with displacements x1 and x2. So straight away, we can solve for the equation of motion. Let's do it. Quick method. M, 0, 0. x1, double dot, x2, double dot. Plus our stiffness, well, we've got the first is the sum of the stiffnesses between mass 1 and the ground and another mass, so that's going to be 2k. For the second diagonal, it's obviously the same thing, 2k. And then here we've got minus k and minus k, the minus sum of the masses of the stiffnesses between mass 1 and another mass. So x1, x2. It's unforced, so this is obviously equal to 0, 0. There's our equation of motion straight away. No need to go through Newton's second law at all. So what you do now is you make the substitution with a trial function. So here I've assumed this. Obviously the other way that I've done it, and you can do this, you can see this in the notes, is you can say xi equals big Xi e to the j omega t. Because we know that it there is the complex form of a oscillation. We know that. So you can make the same substitution and you get the same thing happening when you have the x double dot, is you have a minus omega squared come out front. Okay? That's what I've done in the notes. This here, this is what I've done on the slides. It's the same thing, it doesn't matter. So on the slides we've got this. Okay, you plug it into the equation, you end up getting this as your equation. Okay, so sorry, if you you can see that x double dot 1 and x double dot 2 is minus omega squared times by this. And you plug that into your equation of motion, you get this. Here's the eigenvalue problem. Minus omega squared times by your mass matrix times by x1, x2, plus the stiffness matrix times by x1 over x2. And then obviously this can disappear because you can divide both sides by it. And obviously 0 divided by it is still 0. We can rearrange that equation into the mechanical impedance matrix. So that's okay, so there we've done it, and then we find the determinant of this matrix. So this equation here is basically those two multiplied together minus those two multiplied together. So there we've got the determinant. You can quite clearly see that this is a quadratic in terms of lambda. And if you do the quadratic formula, you get 2 plus or minus 1 k upon m. So that obviously equals k upon m or 3k upon m. And so omega 1 is the square root of that, and the square root of that, and the square root of that. So you get these two natural frequencies, omega 1 and omega 2. And then to find the mode shapes is you stick these back into this equation in place of omega, and then you can solve to find that vector. So there's the general form. Okay, so that's the mechanical impedance matrix, and then we have 1 over r here. So when you've got omega 1, which is root k upon m, omega 1 squared is obviously k upon m. That's going to be m multiplied by m, you get mk upon m, which equals k. And so all of these things will be in terms of k, so we can get rid of k. We can divide the whole equation by k, and you end up with just numbers. So we've got 2 minus 1, minus 1, minus 1, and 2 minus 1, so you end up with this nice equation. If you multiply that by that, you end up finding that R1 is 1. So the first mode shape, I've got it on here. The first mode shape, let's write it here. So I write mode shapes like this. So it's x, 1, so that's the first mode shape. 1 is outside of the braces. 1, 1. So the first mode shape is the two masses are moving in the same amplitude in the same direction. So the spring in the middle isn't doing anything at all. And I'll show you that in a second. We stick in omega 2 to solve for omega 2. Let's go through. Omega 2 is 3k upon m, or root 3k upon m. You stick it into the equation. M times omega 2 squared, you get 3. Okay, so now we have minus 1, minus 1, minus 1, minus 1. 1 over R2, okay, and you end up finding R2 is minus 1. And so now if mass 1 moves to the right by a certain amount, mass 2 will move to the left by a certain amount, the same amount. And so you have the two masses going backwards and forwards. There's your two mode shapes. And so here's an example. A is the first mode shape, where you've got the spring in the middle that's doing nothing. The two masses are moving up and down the same amount in the same direction. Okay? So the only springs that are having any effects is this spring and the spring at the top. That one in the middle is doing nothing at all. Okay, it's not deflecting whatsoever. The second mode shape, however, is the masses are moving together and apart, okay, the same amount. So if mass 1 moves in by amount x, then mass 2 will move in by about x, and then obviously they'll go apart by x, okay, which is what's indicated. This is where you've got a mode shape of 1, 1, and here we've got 1 minus 1. And so sticking those values into the general solution, so we've got C1 times the first mode shape, cosine, there's our omega 1, root k upon m, times by t plus phi 1, and then C2 times by our second mode shape, cosine of omega 2, which is 3k upon m square rooted, times by t plus phi 2. And these terms, C1 and phi 1 and C2 and phi 2, are constants that we can find from initial conditions. We did this back a little while ago. Okay, you stick in your initial conditions, you can find those terms. The other way to write this equation, well, I've not got it in here. It doesn't appear. Well, that's fine. I'll deal with it in a second. So that's what you have when you've got a general 2-degree of freedom system where everything is connected to ground. There's another type of system that we deal with where things aren't connected to ground, okay? And this is called a semi-definite system. The other way you may hear of it talked about is a degenerate system, okay? Where this is a 2-degree of freedom system, but there's only one spring, okay? And you can go through the same process to solve the equation of motion, which looks like this, okay? So there's our two masses in the diagonals. Obviously the springs connecting each mass to ground obviously don't exist, so the only springs you're considering are the ones connecting each mass to each other. Okay? So there's our mass matrix times by acceleration plus the stiffness by our displacement. And you can then stick in the same substitution that we made earlier. Simplify it out. And there's your mechanical impedance matrix. You find the determinant of that matrix. Okay, you end up with this. And notice that what happens when you find the determinant is you end up with this loose omega-2 term out here. So the only way this equation can hold true is if either omega-2 equals 0 or this lot equals 0, because obviously this whole thing equals 0. So omega-2 equals 0, sorry, omega squared equals 0, or this whole lot equals 0. So what we have is we have what's known as the 0th mode, or the 0th natural frequency of 0. Okay? And the second one, or the first natural frequency, is basically when you set this equal to 0, you can solve it, and you end up with this equation. And obviously the square root of this will be omega-1. This is called omega-0. What do we have if we've got no frequency? We've got no oscillation, okay? Things not oscillating at all. So basically, a degenerate system where you're in the 0th mode, imagine this thing is floating around in space, it's just going to float around in space like that. Okay, the two masses are just going to move in unison with each other, okay? But obviously the first natural frequency will have an amplitude, okay, and so that's when the things are oscillating. It could also be moving around in space, but they're oscillating with respect to each other. And how much they're oscillating is going to be determined by the ratio of the masses. What's interesting is if you look at this equation, and you see mass 2 is huge compared to mass 1, okay, you end up with k upon m being the root k upon m being the frequency. Okay, because this is very small compared to that, so that would be k times m2, and this will be, yes, sorry, that's right, yeah. If you do the sums, you come out with root k upon m, I'm sure of that. Yes. If mass 2 is ginormous compared to mass 1, then you've got k times m2 over m1 times m2. The m2's cancel, and so you end up with k over m1. So there's your natural frequency straight away. Because essentially mass 2 is essentially like ground then, okay? Mass 1 is what's oscillating. So substituting the values for omega back into that impedance matrix, we can get the mode shapes. And so when you stick in omega 0, obviously you get R0 to be 1. So your mode shape, your first mode shape, is 1, 1. That's the two masses moving in unison with each other. The spring in the middle isn't doing anything at all. You stick in the second one, your mode shape for the first R1 is the ratio of the two masses, minus the ratio of the two masses. So if mass 1 and mass 2 are the same, obviously you have a mode shape of 1 minus 1. Obviously if mass 2 is greater than mass 1, then you have a mode shape of 1 and then minus some fraction. So that's a degenerate system, and we'll talk a little bit more about that when we talk about the 3 degree of freedom system. But basically it's the same process, it's just that it so happens that this time nothing's connected to ground, and you have that omega 0 situation where there's no oscillation. So this equation is what we saw before, except for I've written in a slightly different way. This is still equivalent to this, the form that we had before, where this bit here equals C1 cosine omega 1 t plus phi 1. Okay? They're the same thing, so obviously what I was writing here. So it's the same as what we were seeing before, except for I've written in a slightly different way. So you can see that that's our solution. And the constants A1, A2, B1 and B2 we can find from initial conditions. Okay, and obviously this is a typical initial condition. Everything's at rest. Generally the initial conditions won't be quite like that because there'll be something that starts the oscillation off. Okay, and so it might be an initial displacement or it might be initial velocity. But this is a typical initial condition. Basically it's everything that's when t is 0. And so you can solve that equation to find x and x1 x dot. Okay, and obviously that's here's the first derivative. We've got this form here. When t is 0, obviously this term cosine omega t becomes 1, sine omega t becomes 0 because obviously sine of 0 is 0, and here we've got cosine omega 2t and sine omega 2t. And then obviously when you do the first derivative you get a minus omega 1 times by the sine, and here you get a omega 1 times by the cosine, and so you get this, a different set of equations. And so when t is 0 you end up with a1 plus a2, because if we go back to this equation, that's 0 and that's 0, so you end up with a1 plus a2. Okay, when t is 0 for this one. That's for x1. For x2, you've got these modes multiplied by a1 plus a2. Okay, and then when you've got the displacement, you stick in 0 into t into this equation. For x1 dot, you've got 1 times b1 times by omega 1 plus 1 times b2 times omega 2, which is there. You stick in t equals 0 into this and find x2. We've got r1 times by b1 omega 1 plus r2 times b2 omega 2, which is this there. So here we've got 4 equations and we've got 4 unknowns, a1, a2, b1 and b2. You can solve to find those terms, plug them back into your general solution, and then you end up with a complete exact solution to your problem.